theorem. And we stated the theorem, but didn't prove it yet. So we'll start today with the proof of the theorem. But I'll state it again just as a reminder. So we're gonna let f be a function with, we're gonna assume that f is continuous on some closed interval, a to b. And we're also going to assume that it's differentiable on the corresponding open interval. Okay, so then what the mean value theorem says is that there is a point in the interval where the derivative equals sort of the average derivative between those two endpoints. So there is, maybe I'll say then, there is a C in the interval, the open interval from A to B, such that the derivative at C is equal to, so I think the easiest way to remember this is to just draw a picture. So if this is A to B and the function looks something like this. So what the theorem is saying is that the slope of this line between A comma f of A and B comma f of B, whatever the slope of that line is, the derivative is actually agrees with that slope at some point inside the interval. So I sort of imagine like, you know, I have like an imaginary pink line and I'll take it like over here, it's parallel to the blue one. And so what this theorem is saying is that if I just like move this towards the graph of the function, eventually this hits it and it's tangent at some point C. That's my like visual interpretation of what this is saying. So right, so what is f prime of C equal to? It's like the slope of the blue line, which is going to be f of B minus f of A divided by B minus A. So this is the slope of that line. Another way to remember what this is saying is that it's saying that there is a number at which the instantaneous rate of change of the function is equal to the average rate of change over the interval A to B. Are there questions about what the theorem is saying before we prove it? Okay, so let's prove the theorem. Okay, so here's the idea. Let me just redraw this little picture. So the function's doing something on that interval, and we have this blue line from A to B. So the idea here is that we basically already have Rolle's theorem, which is the mean value theorem for the special case when f of A equals f of B. So when this is horizontal. So what I'm going to do is I'm going to adjust this function so that it is something I can apply Rolle's theorem to. So what I'm going to do is like write a new function that basically just untilts this blue line and drags the rest of the function down with it. So here's the like idea is I'll define a function h that we can apply Rolle's theorem to. Okay, so what is H going to be? H will be the difference between the function f and the blue line. So it'll be like measuring that height right there. So this is like, H is going to be measuring those differences between f and, let's say, L. So I'll call this thing L. So H is equal to f minus L. And H will have the property that H of A and H of B are both equal to one another and they're zero. So what I need to do is write an equation for this blue line L. And then the equation for H will be given by taking f minus the L. So let's find an equation for L. So how could we do that? Yeah. So just, point slope form and the two endpoints. So we get y minus f of A is equal to, so this will be the slope, which is f of B minus f of A divided by B minus A, and that's times x minus A. So this is just point slope form for that line. Okay, so then I'll just rearrange this. So we get L of x is equal to f of B minus f of A divided by B minus A times x minus A plus f of A. Okay, are there questions about this L of x? So then I'm going to define H to be f minus L. So H of x to be f of x minus L of x, which is f of x minus, I'll just copy all this stuff. And the minus sign also needs to be over here. Okay, so that is H of x. And so what I'm going to do is apply Rolle's theorem to H of x. So what I need to do is verify those three hypotheses for Rolle's theorem. Would it be helpful for me to scroll back to Rolle's theorem so you can like see it again? So okay, so here's what Rolle's theorem says. So if f satisfies these three hypotheses, so we want it to be continuous, differentiable, and have equal values on the two endpoints, then there is some number c such that the derivative at c is equal to 0. So that was the statement of Rolle's theorem. So to use Rolle's theorem on H, we need to verify these three things. So let me go back to, so let's verify that H satisfies the hypotheses for Rolle's theorem. Okay, so why is H continuous on AB? The difference of two functions are each of those functions. Yeah, so why is F continuous? That was actually yeah. So F is continuous just by the hypotheses of what we're trying to prove. So we assumed from the get-go that F was continuous, right? So we're assuming that F is continuous and F is differentiable. And then what about this part? Why is L of X a continuous function? Yeah. 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 So like, let's think about this L of X for a second. This, like, it looks messy, but if you think about it, these are just numbers that we're plugging into here. So this is just like some coefficient, and this is just also some number. So all this thing is a line, and we know that lines are continuous. For example, because like polynomials are continuous, and this is just a special case of that. Okay, so H of X is a continuous function minus another continuous function, so it's also continuous. So since it is a difference of continuous functions. And then why is it differentiable on the interval from A to B? So not all continuous functions are differentiable, right? Like be like pointy, but we assumed already that F was continuous and that F was differentiable. And we also know that L is differentiable, right? It's just a line. We know how to take the derivative of that. So it's like same reason as here. We know that H is a difference of two functions that are each differentiable. So this is since F and L are differentiable. Okay, and then H of A equals H of B. So for this, we'll just check this. So we'll just plug in A and plug in B and make sure that we get the same answer. So H of A is equal to, I'm just plugging into this line here. So this is going to be F of A minus F of B minus F of A divided by B minus A times A minus A minus F of A. Okay, so what does this simplify to? Zero, yeah. So this is zero, so this part goes away, and then that and that cancel each other. So we just get 0 here, and then let's compute H of B. So this is going to be F of B minus f of b minus f of a divided by b minus a times b minus a minus f of a. Okay, so here we have to do a little bit of work to simplify this. So the b minus a here and the one in the denominator cancel each other. And then I will have to distribute this minus sign into these two terms. So I get f of b minus f of b plus f of a minus f of a, and then this is 0. Okay, so that verifies this last bullet point. Okay, so then now we know that we can apply Rolle's theorem because we know that H satisfies those hypotheses. So let's see what Rolle's theorem tells us. So by Rolle's theorem, there is some number C inside of the open interval from A to B such that H prime of C is equal to 0. Okay, so then let's see what that's actually telling us. So what is H prime of C? So let me go grab H again, and we'll take the derivative of this. Oops. Okay, so H of X is this. So what is H prime of X? We don't have an equation or anything for f of x, so this will just be f prime of x. And then what about the rest of this? What is the derivative of this expression? Let me rephrase this. So like secretly, this is like some line, right? So I can think of this as like some number, like a constant k times x, minus some other value, let's say m. It's like a line, so just kx plus m. So if I wanted to take the derivative of this, I'd just get k, right? So I just need to know like whatever, what is the coefficient on x, which is this stuff. So we just get, yeah, so just this, yeah, so if you take the derivative of a line, you just get the slope. Yeah. So this is minus f of b minus f of a divided by b minus a. Okay, so Rolle's theorem told us that this quantity was 0. So let's rearrange this. Oh, sorry, if I plug in c, so we get 0 is equal to h prime of c, which is equal to f prime of c minus this stuff, f of b minus f of a divided by b minus a. Okay, so now I'm just going to rearrange the equation, so I'll forget about this middle part. So I'll just solve for f prime of c. We get f prime of c is equal to f of b minus f of a divided by b minus a. And that finishes the proof because that's all we wanted, right? We wanted to find that there was some value c for which the derivative of f at that value was equal to this slope. So like, to recap, like what happened just in a picture. So we started with this f and this line. And then we made a new function called h, which sort of like untilted this thing, but also drags it down to 0. So this is h. And then we used Rolle's theorem on h to find where the derivative of h was 0. And then at that same value, so whatever this c is, at that same value here, we'll get that the function f as derivative parallel, like agreeing with the blue line. Is this making sense? Are there questions about the proof or about the theorem? Yeah. Yes. Yeah, so like find a C where the derivative equals something. Yeah, okay, so we can do that. Let me think. Yeah, so let's do an example. What do we want F to be? I think if it's a line, it's not going to be super interesting because the slope will be constant on the whole thing. So any number C inside of there will work. Yeah. Yeah, okay, so let's do x squared. On, let's say the interval from 0 to, how about 0 to 2? Okay, so we have something that looks like this. Sorry, so f of 0 is 0, and then f of 2 is 4. And f of 1 is 1. So it looks something like that. Okay, so let's find where we'll find the C that the mean value theorem tells us exists. So we want to find the C such that f prime of C is equal to the slope of this blue line, which is f of 2 minus f of 0 divided by 2 minus 0, which is equal to 4 over 2, which is 2. Okay, so is the problem statement clear? So we can just find f prime of C. So, or sorry, f prime of x. So f prime of x is equal to 2x. And then what we want is to find the C such that this is equal to 2. So we want to, maybe I'll put in C. We want 2C to equal 2. So then C is equal to 1. So at this point, the derivative agrees with the average derivative. Yeah. Yeah, so if the problem, so there in the web work, there's some problems that just say something like find the C that was given to you by the mean value theorem. So yeah, you would need to compute like what is the slope. Like, this is like the slope of the blue line, and then C is like the value, the x value where the function has derivative equal to that slope. Yeah. Because we want to find where the derivative equals the slope of the blue line now. So that's why yeah, 2C is 2. Okay, let's see so like, I think, just from the statement of the mean value theorem, it's maybe not clear why it might be interesting, but it is actually very useful for proving a lot of different statements. So we'll talk about some consequences of the mean value theorem that are actually like more useful than the original statement. So consequences of the mean value theorem. So here's one corollary. So a corollary is like something that is very easy to prove once you have the proof of the more difficult like theorem. So in this case, the mean value theorem is the theorem, and then this will be like an easy consequence of that. So here's the corollary. If f prime of x is equal to 0 for all x's in AB. Okay, what's the intuitive conclusion of this? Like, suppose I give you a function and I tell you that its derivative is 0 everywhere. What does that function look like? Yeah, it's just going to be a constant function. So maybe it's not clear how to prove that without yeah, I don't know, it's like intuitively true, but it's like hard to say why. So and I guess I should say, so if f prime of x is 0 for all x in AB. So in this statement, it's implicit that f is differentiable for all x in AB, which will also imply that f is continuous. So it's like sort of implicit in the statement that f is continuous and differentiable on that whole interval. Okay, so then f is constant on AB. So we can prove this with the mean value theorem. So here's the proof. So I'm going to let x1 and x2 just be any two numbers from the interval. And I'm going to make sure that x1 is less than x2. Then what we'll prove is that f of x1 is equal to f of x2, right? Because if I pick any two numbers in the interval and f has the same value at those two numbers, then that means that across the whole interval, f will be constant. So we will show f of x1 is equal to f of x2. Okay, so here's why. So we know that f is differentiable and continuous on the whole interval from x1 to x2. So then the mean value theorem tells us, which I'll just abbreviate it MVT, the following. So it says that there exists a C inside of this interval such that f prime of C equals the slope of the line from x1 comma f of x1 to x2 comma f of x2. So we get f of x2 minus f of x1 divided by x2 minus x1. And we also know that the derivative of the function is 0 everywhere inside of this interval. So in particular, f prime of C is also equal to 0. So then I can just rearrange this. So if I multiply both sides by x2 minus x1 of this equation, then I get that f of x2 minus f of x1 is equal to 0, which tells me that f of x1 is equal to f of x2. And that finishes the proof of the corollary. So this is maybe not so impressive because the statement was maybe at least on an intuitive level kind of obvious, but here's something that we can do with this statement that is maybe less obvious. So this is like a corollary to the corollary. So let's say I have two functions now and their derivative equals one another everywhere inside of some interval. So if f prime of x is equal to g prime of x for x's in some interval, then what this is going to say is that the functions f and g actually only differ by a constant. So then f minus g is constant on AB, which you could rephrase as f of x is equal to g of x plus some number, let's say k for constant. Okay, so why is this a corollary of the previous corollary? So let's prove it really quick. We know that f prime of x minus g prime of x is equal to 0 just by this hypothesis, right? The derivatives are equal, so if I subtract them from one another, I get 0. But this is also equal to the derivative of the function f minus g. So this is f minus g prime of x. So that tells, so then the previous theorem says, okay, if I have some function, has a wacky name, but if I have some function and its derivative is 0 everywhere, then that means that the function itself was constant. So by the previous result, we get that. So by the previous result, I find that f of x minus g of x is equal to some constant. And that's the proof of the corollaries that finishes this. Okay, are there questions about this? Okay, so there's more that we can do with the mean value theorem. So it can also sort of tell us about what the derivative of a function tells us about the shape of a graph. So back a long time ago, we sort of already talked about this, but now we'll phrase it as like an actual test. So I'm going to call this, what do derivatives tell us about the shape of a graph. So we know that the derivative represents the slope of the graph at that point. So if I have, I'll just draw a little picture. So if the slope is something like that, so we've spoken before about how, if this slope is a positive number, then that should tell me that the function is increasing right there. And on the flip side, if the slope is negative, so something like that, then that should tell me that the function is so now we'll be able to, using the mean value theorem, we'll be able to prove that more rigorously. So let me phrase this as a test. This is called the increasing/decreasing test. So part A deals with when it's increasing. So if the derivative of a function at x is greater than 0 on some interval, then that means that the function is increasing on the interval. Let me say what increasing means. I think we have like an intuitive understanding of what this is, but like to phrase it precisely, this means that if I have x1 less than x2 coming from the interval, then that means when I take f of those, f of x1 should be less than f of x2. Right, so if I take any two numbers from the interval and I compare the values of f on them, the one to the right should have the larger f value. That's part one of the test, and then part two will be for decreasing. So B, if f prime of x is less than 0 on AB, then the function is decreasing on AB. So meaning if I have x1 less than x2, now the inequality will be flipped. So if we're decreasing the function, the value should be getting smaller. So f of x1 is now the bigger one. Okay, are there questions? Yeah. Yes, so we'll prove it and the proof will rely on the model. Yeah. Yeah. Are there other questions? So okay, then let's do the proof and then we'll do examples probably after spring break. So let's see the proof of this. We will just prove part A because part B will be similar. So we'll prove A only. So let's let x1 and x2 be numbers in the interval from A to B. And let's assume that x1 is less than x2. Okay, so then what we need to show is that the value of f of x1 is less than the value of f of x2. Okay, so what does the mean value theorem tell us in this case? So let's just see. So by the mean value theorem, there is a C in the interval from x1 to x2 such that f prime of C is equal to f of x2 minus f of x1 divided by x2 minus x1. Okay, so what do we know? We know that this number is positive, right? Because we assumed that the derivative was positive on this interval. So we know that this is greater than 0. We also know that x2 minus x1 is greater than 0 because we took x1 to be less than x2. So we know f prime of C is greater than 0 and x2 minus x1 is greater than 0. Okay, so I get some inequalities. So from this one, I get that f of x2 minus f of x1 divided by x2 minus x1, that's all greater than 0. And then since x2 minus x1 is greater than 0, I can multiply both sides of this inequality by this quantity, and it doesn't flip the inequality. So by the second one, we get that f of x2 minus f of x1 is greater than 0 times x2 minus x1, which is just 0. And then just rearranging this, we get f of x2 is greater than f of x1, which is what we wanted to show. Okay, are there questions about that? So I feel like the mean value theorem is kind of sneaky, where like whenever you have these statements that like sort of relate the derivative and the values of the function, it may on some level not look like the mean value theorem is involved, but then it does like appear in the proof. And I think that is like sort of its power, right? Is that it gives you a way to relate the derivative of the function somewhere to the actual values of the function in some way. So in my mind, that's sort of like why it's useful, but yeah, are there any questions? So we'll pick up after spring break. I'll remind you of these tests and then we'll do some examples.